Let's look at an example of using the sampling distribution for the mean. This is based on problem 24 in chapter 18. And this is a really big deal because it's the first time it's the first time we use what's called the Central Limit Theorem in its usual version that tells us that the normal distribution comes into a situation whether we start with it or not. And it's also a really good bridge to the ideas of confidence intervals and hypothesis testing, which are the core of how we do inferential statistics in the rest of the book. So mainly I'm going to go through the example, but I'm going to make some comments about the ideas as we go. So suppose that home values in Albuquerque, New Mexico, have a mean value of $120,000 and a standard deviation of $50,000. Okay. And let me point out something that's a bit unrealistic about this, and it's one of the crucial things we're going to change later. This is assuming that we know the precise data for the entire population. So maybe a careful census has been done at great expense to get this information. And in fact, what I'm going to assume is we even know the distribution of the homes. And let's say the mean is 120,000 and it's skewed a bit maybe to the right. And that's realistic for anything that has to be positive but can get pretty high. Skewing to the right is pretty common. So there's going to be a few really, really expensive homes, and then the bulk of them are actually maybe a bit under 120,000, but the mean actually ends up being 120,000. Okay, so this is kind of weird that we actually know the precise data for the entire population, and then it says we sample 100 homes at random. Why on earth would we do that? We already know everything there is to know about the population. The answer is that we're warming up for sort of flipping this and reversing the situation, where we're going to imagine in the next chapter and beyond that we sample and we know the data in the sample, and we don't know these key numbers, especially the 120,000, and we'd like to figure out what that number is, the 120,000. Okay, it's a little too hard to jump all the way to there, and so we're going to have this slightly artificial thing where we assume we know the population data, and then we're going to look at a sample and see what would happen with the sample. Believe me, it's a crucial intermediate step. Okay, so we sample 100 homes at random. That's of course crucial for all of this to work. And we want to describe the sampling model for the mean value of homes selected. So remember what that is. It's a subtle thing. It's not going to be this distribution. We're not asking for this distribution. And we're also not asking for what is the histogram of this particular sample of 100 homes. It would give us a certain, 100 numbers, a data set, and we could draw the histogram of that single data set. But that's not what we're asking about. What we're asking to do is we imagine doing the same sample, doing the same procedure, doing the procedure of sampling 100 homes randomly many times. Okay, we don't actually do it, but we imagine doing it. Again, you might ask, why are we doing that? Why are we imagining this? Well, really the payoff is in the next couple of chapters, where we are trying to go backwards from the sample of the population. But let's bear with it for a minute. We imagine doing the procedure of sampling 100 homes randomly many times, and for each one, we only record one piece of data, a statistic. One statistic that's just we know that's a summary piece of data from a bunch of actual raw data, and that's the mean. And it just happens to be that that's the statistic we're interested in right now. We could record other things, proportions and standard deviations and all kinds of stuff. But the simplest place to start is the mean. That's where the central limit theorem applies. Okay, so for each one we only record one statistic, the mean, and then what we imagine the sampling model for the mean is what would the distribution of all those statistic values be. So if we keep doing 100 different random samples of 100 homes, we're going to keep getting different averages. They're not usually going to be 120,000, even though secretly they kind of should be. That's the ideal value, but they're not. There's randomness. But they should cluster around 120,000. How do they cluster? That's the thing. Okay, so the key is the central limit theorem. And that says, under the appropriate conditions, the sampling distribution of the mean is very well approximated by a normal distribution, and we'll say what particular normal distribution in a minute. Okay, that's why I have this nice colorful picture I got off the web of a normal distribution. Okay, that this guy, when we sample the average of a bunch of samples over and over again, we actually will get this distribution. I don't know if you can see my cursor up here. I'm pointing to the nice colorful bell curve. Okay. All right, so let's look at the assumptions. Okay, we need to check that the sample really is random. Okay, so we're trusting that the sampling procedure was done well. That's one reason why we've already discussed design of experiments and samples and things like that. Okay, it's got to be random, or else all of this, none of this stuff applies. Okay, and we've got to have independence. Okay, so if this is a truly random sample and we're just pulling things out, pulling homes out of a list of homes, that will be independent if we have the 10% rule satisfied. The only thing that could go wrong there is that we don't want to sample so many homes that the stock is kind of depleted, is significantly depleted. The analogy I always go back to is getting cards out of a deck. Okay, if I draw 30 cards out of a 52-card deck, I'm going to affect the probabilities of what I get after that. Okay, usually the 10% rule isn't an issue because we're not usually so rich that we sample a large number, a large proportion. In this case, there's a lot of homes in Albuquerque, and 100 homes is definitely less than 10% of that. Okay, and then the other thing we need to know is the large enough sample. So that was the 10% rule is don't make the sample ridiculously large. And we didn't, okay? And the large enough sample rule, unfortunately, isn't super hard and fast for the central limit theorem. There's not a simple rule we can use. But the very rough rule of thumb is if the actual distribution of the population, that's this guy, the actual histogram that we usually don't have access to, but we're being a little fake and giving ourselves access to it, is already unimodal and symmetric, kind of getting close to normal-ish, then something like 10 or more sample size is okay. In this case, it's not symmetric. It's been stated to be skewed, and we can see that it's not really very close to a normal distribution. It's not horrible, okay? But guess what? We've got 100 samples, 100 homes in each sample. That's much more than 10. 100 should be okay here. Okay, it would have to be a ridiculously bad distribution for 100 to be give us really bad approximations. It's unfortunate that we can't say too much more here. To say more, we'd have to get into some pretty subtle things about the statistics, about the mathematics. Okay, so that means that the CLT applies. Okay, and what we get is a normal distribution. All those possible hypothetical means that we could get out of these samples, it's normal with the mean being, well, guess what? Exactly just the mean of the population, 120,000. And standard deviation, well, it's the population's standard deviation, call that sigma, just divided by the square root of n. Okay, we saw that with the proportion example, that the square root of n is the key factor, and it's the same deal. 50,000. I guess I'll put the comma in there. Sorry, it's kind of distracting. Divided by the root of 100, and so that's $5,000. And suddenly I'm in math mode. Yay! Okay. Okay. So now we can be more explicit. We've got a normal distribution with mean 120,000 and standard deviation 5,000. So let me see if I can ink on here. So here, this is going to be. I haven't tried this. 120. Let's do it in thousands, so I don't have to write a lot of zeros. And then mu plus sigma, okay, one standard deviation. That's going to be 125. Okay. And then mu plus 2 sigma is going to be 130. And here it's going to be 135. That's not so bad. I'm actually doing this with a mouse, not a stylus or anything. Here it's going to be 115. Here it's going to be 110. And here it's going to be 105. So remember, I'm not saying this is the distribution of values of homes in Albuquerque. What I'm saying is that if I do these samples, on average I'm going to get something close to $120,000 for the average of the 100 homes in the sample, the values. But I could easily get something up as high as 125 or low as 115, but with pretty low probability it's going to get up to 130, 135, or down to 110 or 105. In particular, let's say 68% of the time, let's go back to here, 68% of such samples will yield a mean between 115,000 and 125,000. Okay, 95% of such samples will yield a mean between 110, forgot the dollar sign last time, 110,000 and 130,000. And a whopping 99.7% of such samples will yield a mean between 105,000 and 135,000. Okay, so let's get down to a very specific question. In B, it says give the probability that the mean value in the sample will be more than $10,000 away from the true mean of the population. Well, guess what? That's exactly answered by the 68, 95, 99.7% rule, by the 95 case. Okay, the probability of this is just 5%. Okay, because 5% of those guys are where we actually get 130 or above or 110 or below. And I want to focus on this question because it's really close to the key question we're really interested in starting in the next chapter. Suppose you showed somebody all this problem, but you just never showed them the real population mean, the 120,000. Okay? And suppose you showed them, you went ahead and did one of these samples, just one, because you don't want to do it over and over again in reality, because that would cost a huge amount of money. You sample 100 of the homes at random, okay? And suppose you get, maybe we get $127,000 as our, suppose one sample yields a mean of $127,000, okay? What should somebody looking at that think? Should they think that that's a pretty accurate estimate of the actual mean of the population? Remember, we're not letting them see the $120,000 that we secretly know about. We just show them the sample mean, and it's $127,000. Should they assume that's a pretty good estimate of the real population mean? Well, we happen to know it's pretty close. It's $7,000 off. Should they, just looking at this 127, should they say, I think 127 is pretty close? Well, they really should be pretty confident that this is not very far off, because they know that if they know the Central Limit Theorem, then they know that whatever the mysterious mean is, in this case it's $120,000, 95% of those guys are within $10,000 of the right answer. That's what this is. The probability of being off by $10,000 is just 5%. So if they see the 127,000, they don't know it's really 120, but they'd be extremely surprised to learn that the population mean was $95,000 or $140,000 or even $112,000 or even $140,000. Okay, this is probably pretty close to the reality. That's what to someone who only sees this sample mean. Okay, and that's the perspective we're going to take starting in the next chapter. We're going to put ourselves in the perspective of not knowing the reality, not knowing the population mean, and only getting this number. But we'll be able to sort of translate this kind of thinking, and it's going to be a pretty tricky inversion, but we're going to translate this kind of thinking into saying that, okay, this can't be too far off because I had a big enough sample, and the reality should be pretty close.